Chapter 6 is all about where the electron is outside the nucleus. In order to know something about the electron, we have to know something about light. The following diagrams represent two electromagnetic waves. Which wave corresponds to the high energy radiation? Explain. All right, so it was James Clerk Maxwell that recognized that there was. Oh no, it was Planck, right? We're talking about energy. It's Planck, right? Planck recognized that there was a relationship between the energy of the wave and its frequency. So if you have a short wavelength, you have a high frequency. That's the Clerk-Maxwell part. So it looks like diagram A has a shorter wavelength. If you have a shorter wavelength, it means you have a higher frequency, which means you have a higher energy. All right, so short wavelength, high energy light. E is equal to h nu. Nu is equal to c over lambda, right? So those are the two guys, right? Planck and Clerk-Maxwell. So I can plug c is equal to lambda nu in for nu and get an equation that directly relates or indirectly relates wavelength to energy, right? So short wavelength, high energy, long wavelength, low energy. The contour representation of one of the orbitals for the n is equal to 3 shell of the hydrogen atom shown below. Okay. What is the quantum number L for this orbital? All right, so what is the shape number for this orbital? All right, so we're looking at the dumbbell shape. The dumbbell shape is the P shape, and it's being orientated along the y orbital. So L is equal to 1. Again, there's 3 orientations for a P shape, X, Y, and Z. This one's orientated along the Y. So 3py would be the orbital that we're representing here. All right, that's B. How would you modify your sketch to show the analogous orbital for n is equal to 4? All right, so n is equal to 4 with a P shape. It'd be the same shape. It'd just be bigger, right, further out. So a bigger distribution further out from the nucleus. An argon laser emits light at 532 nanometers. What is the frequency of this radiation? Use figure 6.4 to predict the color associated with this wavelength. All right, so like we just saw before, there's a relationship between wavelength and frequency. So if I rearrange lambda nu is equal to c, divide both sides by lambda, I get a relationship between lambda and nu. So I can plug this into the equation as long as it's in meters, right? C is the speed of light, 3 times 10 to the 8 meters per second. So the first step would have to be to convert nanometers to meters so that I can divide it into speed of light. Now I can divide meters into meters per second, which is the speed of light, cancel meters, and get per seconds. Per second is the unit for frequency. And if we're talking about the visible spectrum, yeah, we're lining up somewhere in the green area here. All right, Roy G. Biv, right? Red being a long wavelength and a low energy light. Oh, I take it back, man. It's going to be the other way. Roy G. Biv. So red, orange, yellow. No, red, orange, yellow, green, right? So we're more up in the green range. Indigo, violet. Okay, green. Calculate the energy of a photon of electromagnetic radiation whose frequency is 6.5 times 10 to the 12 per seconds. All right, so we have a high frequency here. We want to calculate the energy. First things first, right? Calculate the energy of the photon if I know what the frequency is, right? So I'm plugging into Planck's equation. E is directly related to frequency. Planck's constant is the constant that equates frequency to energy, right, in joule seconds. So 6.26 times 10 to the minus 34 joule seconds times per seconds will cancel seconds, and I'll be left with joules. Calculate the energy of a photon whose wavelength is 322 nanometers. All right, so again, we could do this in two steps, right? We could use C is equal to lambda nu to solve for what the frequency is and then plug in a Planck's equation. Or I could combine the two equations, right? E is equal to hc divided by lambda to get a relationship between wavelength and energy. All right, so in part B, calculate the energy of the photon of the wavelength when you have 322 nanometers. I can plug into the equation. So the trick here is making sure all the units are correct, right? So Planck's constant is a way to go from joule seconds to joules. Planck's constant's in joule seconds. C, speed of light, is in meters per second. Therefore, you have to put your wavelength in meters. So this is the trick to the problem. So make sure that you convert from nanometers to meters. There's a 10 to the 9 nanometers for every meter. So now that you're in meters, you can divide meters into meters per second and cancel meters. Multiply meters per second by joule seconds, cancel per seconds, and you're left with joules. All right, with C, what is the wavelength of radiation that has photons of a certain energy, right? 2.87 times 10 to the minus 18 joules. So we're just rearranging this equation, right? Multiply both sides by wavelength, divide both sides by E, energy, and we get an expression where I can plug energy into the denominator, divide it into the constants h and c, and get the wavelength in meters. So I've got h, I've got speed of light divided by joules. Joules will cancel, per seconds will cancel, and I'll be left with how many meters this wavelength is. So this is a ridiculous fraction of a meter, so better to put it into nanometers. So for every 1 meter, you've got 10 to the 9 nanometers, so multiply by 10 to the 9. We have 69.2 nanometers. 25. Calculate and compare the energy of a photon of wavelength 3.3 micrometers with a wavelength of 0.154 nanometers. Use figure 6.4 to identify which region of electromagnetic radiation it belongs to. All right, so micrometer, nanometer, right? Micrometer is a millionth of a meter. Picometer is nanometer is a billionth of a meter, and micrometer is a millionth of a meter. So that's the relationship to meter, right? So 10 to the 9 versus 10 to the 6. So there are 3,300 nanometers for every 3.33 micrometers. So I can plug into E is equal to hc divided by lambda, solve for the energy, and then compare that to the other one in nanometers, 1.156 nanometers. So the one that was in micrometers is a lot less energy than the one in nanometers, right? The shorter the wavelength, the higher the energy. So what regions are we talking about here? All right, so 3.3, everything should be in nanometer. Okay, so we got it in nanometers. So we're talking about the infrared range, right? So a wavelength that's longer than 750. We're talking about 3.33, right? 3.3 times 10 to the 3 nanometers. The electron goes from n is equal to 4 to n is equal to 2. Range. All right, so anytime you're coming from a high energy state to a low energy state, you're releasing energy. So coming from an N back to a 2 is going to release a certain quantum of energy in the green range, right? Move from 3 to 2 gives you a red line, and move from the fourth energy level to the second gives you a green line. From an orbit radius of 2.1 angstroms to one of 8.46 angstroms. So if the electron's going further out, you'd have to absorb energy to do that, right? To make an energy jump up to a higher energy level, you got to put energy in, and that'll make it jump. So it's an absorbing process. C, an electron is added to H plus ion. Well, H plus ion is hungry for electrons, and there's an attraction between the H plus ion and the electron. So anytime a hydrogen grabs an electron, it'd be a releasing process. (51) N is equal to 4. What are the possible L values? All right, so these are the different quantum numbers, right? The L number, the N number, principal quantum number, the L number, the angular momentum quantum number or shape number, and the ML number, which is the orientation number or magnetic quantum number. So you need all three numbers to get an address. So if N is equal to 4, there are 4 shapes associated with the fourth energy level. A 0 shape, a 1 shape, a 2 shape, and a 3 shape. Or another way of saying it, an S shape, a P shape, a D shape, and an F shape. L is equal to 2. What are the possible orientations? Well, it goes from -2 to +2. So 5 orientations for a D shape. -2, -1, 0, 1, and 2. What are the possible shapes where you've got an orientation of 2? Well, anything 2 and up. All right, so you introduce the 2 orientation with the 2 shape. All right, so from then on, there's a 2 involved with the orientation possibilities. 53, give the numerical values, N number, the principal quantum number, the angular momentum quantum number for each of the following designations. All right, so 3p, that's the third energy level. A 0 shape is an S shape. A P shape would be a 1 shape. So those are the quantum numbers that correspond to 3p. 2s, second energy level, S shape, which is a 0 shape. Fourth energy level, F shape. Well, in the fourth energy level, there's a 0 shape, a 1 shape, a 2 shape, and a 3 shape. All right, so the 3 shape is the F shape. A D shape is a 2 shape in the fifth energy level.